This exponential function, then, where the independent variable x is in the power, which we've mentioned already, of the form y equals ab to the x, something like that. In this case, look, this is a special case that we'll be coming on to when we get on to calculus. The special cases where the rate of change equals the value of the function, and more on that when we look at it. And this is a very important function. If we think about things like biological cultures in dishes, the rate of increase is equal to the size of the amount of cells you've got in there, or with some constant in there. If the rate at which something changes depends on how much you've got, that's this special exponential case where the base turns out to be this natural number that we call e. And it's the natural number occurs all the time in these sorts of things, like the decay of a calculator, or biological growth of cells, or human population growth. Anything that behaves like that naturally, hence the name natural number, has this number e as the base. So as a final exercise, we've got a set of data here where it's believed that the law is of the form v equals v e to the t over tau. T over t rather. And so we can do a similar experiment to try and prove that that's the case. But we do, especially, because we suspect it's the base e, we use not normal logarithms to the base 10, but what are called natural logarithms, which are to the base e. So if we suspect this sort of function, we use the natural logarithm. So let's take this function, v equals v naught, I think it was, wasn't it? V equals v e to the t over t. V equals v e to the t over t. Now we take logarithms to the base e, the natural number. Of both sides. And log to the base e, because we use it so much, is abbreviated to ln, the natural logarithm, ln. And you've got an ln button on your calculator. So if you're suspecting an exponential function with the base e, then you would use the ln button, not the log button. So let's take our function, v equals v e to the t over t, and take natural logs of both sides and see what that does. Therefore, the natural log of v equals the natural log of v times e to the t over t. So same thing, take log of both sides. Same laws apply for natural logarithms as does for any base, so we can turn a multiplication into addition, and we can bring the power down. So log v equals log capital V plus t over t times the natural log of e. And then we can say why it is that we do this, because if we just think for a minute about logarithms again, and it is the logic is a bit tortuous around it. It's the first time you come across it. Remember what a logarithm is. It's a power to a base, a power with a base. So what is the number that I have to raise 10 to give 10? 1, right. So if I'm finding the logarithm of the base, the answer's 1. What's the power to which I've got to raise e to get e? 1. And so therefore, the log to the base e of e is 1. And that needs a bit of thinking about to do with logarithms, and you might not quite see it now. You might not really see it, but you accept. They're like opposites of each other. If I find the logarithm of a number and then find that number to a power, I actually end up back at 1 again. They're like inverse functions, is another way of thinking of it. So if I find the logarithm of 10, the answer's 1. If I find the natural logarithm of e, the answer's 1. So that turns out to be 1. And we end up with just this. Log v equals log v plus t over t. So now, if we think of our original function, we were plotting, if I write this slightly differently, and log v equals, let's write this as the constant, which is 1 over t, times t, which is the variable, plus log v, which is a constant. So we can now compare this with y equals mx plus c, like we've done before. And now if I plot log of v against t, I should get a straight line. The gradient will tell me 1 over the constant capital T, and the y-intercept will tell me log of capital V. So that again allows me exactly the same procedure now to find the constants capital T and capital V.